Welcome. Okay, now last time we saw how to extend our FizzBuzz program to deal with multiples other than 7 and other than 3 and 5. So we added 7 and 9. And along the way we ended up with this expression for our test function, where we apply all the tests. And we saw, it works, but if we were to add more and more um, no, tests, so we want to say multiples of 2, multiples of 6, what have you, it wouldn't, it doesn't become, it's not more, the expression is no more concise, it's no longer concise. So what we can do is we can replace this by a much nicer expression using lists as follows. And then we just have more 3, more 5, more 7, and more 9. Okay, and this will basically, excuse me, this expression is equivalent to the one we had before, but it's much concise because we're just basically folding the nabla operator over the list of tests. So for example, to add another test, all we then need to do is just, in fact, before we go into that, let's just confirm that it works. Okay. Did that build? Let's try again. Yeah, that built. And did this? It should have been, of course. And then I forgot to actually apply the function to the end. Okay, and let's build that. So it's good to. There we go. And if we run it, you can see we still got FizzBuzz Bass, and there's our FizzBuzz. So it works. And then if we want to add another one, we could just do, so if we want to add 2, we could just do mul 2 equals mul of 2, I don't know, faz, and then if we just add mul 2 n, and we build. And there we go. Yep, there's fast. 104 is multiple of 2, so we get fast. So of course, 100 is multiple of 2 and it's multiple of 5, so we get fizz. That's like FizzBuzz. And that, excuse me, and that really should be it. Really, I mean, I think that's that's really as nice as we can go almost. Because now in order to add things, it's very, very easy, it's very clear, and yeah. But there is one thing we might want to do. Okay, suppose we didn't want to use, or we didn't want to, you see, if we didn't want to limit this to lists, okay? So we wanted, for example, it to be in Haskell. There is a type class traversal. In fact, if I come here, can I do traversal? Yep, okay, traversal, there it is. And basically, what a traversal is it can be any data structure that is traversable. It could be a list, or it could be a sequence, or it could be a set, or what have you. Now, this will only work on lists, because fold_r_want is a list function. So, if we wanted to do a fold for any traversable, we would have to use the function. And let's see if I can find it. Nope, it won't do. Okay, I'll do import data dot traversal, and if I do fold, oh no, where is the fold? Or is it, where would it be? The fold function. Hold on, let me see if I can find it. If I go to go to Google. Just a second, I'm just using my phone for this. If I go to a search for fold, it's in data.foldable. So if I go to data.foldable, yes, and then I do fold, yeah. Okay, so in fact, sorry, it's not reversible, it's foldable. Okay, so let's start again. So what I do is I've used the list fold in order to fold, fold the nabla operator through a list. But suppose I don't want to specify that it must be a list. So I would like to be able to use any data structure that I want. The only constraint is that it should be foldable. I should be able to call fold on it. So that's no problem. I can use the function fold, and it will take the list of whatever my thing is, and it will turn. So in this case, it would be a FizzBuzz. So it will take a foldable of FizzBuzz, and it will turn a FizzBuzz. But there has to be a constraint. The constraint is that my FizzBuzz must be an instance of the Monoid type class. So how do we go about doing that? Okay, we'll come back up here, and we'll do instance Monoid FizzBuzz, where now there are two functions we have to. If I do Monoid, yes, there are two. It says minimal mmT mappend. So there are two functions basically I need to implement: mmT and mappend. mmT is the unit of our monoid. So remember, we established that the unit element of the FizzBuzz type would be numint. So we can do mmT equals num. Then what do we put here? Do we put num0? Well, but then that wouldn't work if that would only work for num0s. So because if we come back down here, can you see it has to be any number n. For any number n, then num of n is the unit element. If I put num0 there, then this will work if basically it will only work for 0. If you put like num5, so then it wouldn't work because num5 and num0 are not the same. So this is an issue. What do I put here? I don't know what I want to say is it can be any number. Like I can't say that. So what do we do? Well, what we do is we will resort to abstraction. So instead of doing an instance for FizzBuzz, what we'll do is we'll create a new type. We'll call this let's go call it T for the moment. And what we'll say, a T is, it takes, instead of a FizzBuzz, it'll take an int, a function from int to FizzBuzz. Okay, all right, and we can make this an instance of Monoid because we can do instance Monoid T, where now m empty, so that's the unit element. Well, that's easy. Now we can just say it should be t. It's the function that takes a number n and then it returns num. There, that allows us to say for any n it should be unit element. That's great. And then the next one we need to implement is m append. That's the next function. And what we do is we have, so I'll write it like this. We have t f, so we got a tf and then m append tg, so it takes two functions, f and g. So for example, it could be in fact, perhaps to make it a bit simpler, I'll say mol x and mol y. Okay, so for example, mol x could be 2 and then mol y could be 3. So you see where these two functions. And what we do is it should give us another t, and that should be found as a function. Again, takes an n. So it takes a number n, and then what does it do? Well, it applies mol x to n, and then it applies, and then it combines it using our number operator, mol y to n. Okay, so that's all. That's it, and that should work. If I build this, let's just check. It's not having a problem. Oh, it's because of this here. Shouldn't be there. Oops. Come on. Oh, I didn't build it. Okay, there we go. That's fine. So there's nothing wrong with our Monoid instance. So before we continue though, we look at something really interesting. We look at this type, int to fumba. Where have we seen that before? Right here. Isn't that interesting? So what that means is we can now change this. We can use fold. We will need to import data that's foldable, as you saw in the foldable. Okay. So, and then it's just going to be now we notice that the monoid is the function type, so it's the function that I'm on, so we're no longer going to apply them. So we just do this. Excuse me. Okay. There. And now, if I build this, what's it saying? Okay, there's no instance for show. Oh, that shouldn't make any difference. Oh, you know what the problem is this is these are functions into fumba, but our monoid instance is of type T. So what we're going to call this, let's rename T, let's call it something nice. We're going to call the type test, and then the constructor we also call test, and then instance monoid test, and then test, and then test, and then test. Okay, and now what we need to do is we need to fold and then map test, because remember these are types, mul2 is of type interfumber, but our monoid is of type test, so we need to change a type of interfumber to a type test, and the way we do it is by applying the value applying the constructor test. So map test will apply the constructor to all these elements, and then we'll have something that we can fold. And then what I could do is, now this of course will be of type test as well. So what I would like to do is, I know what I can do. What I will do is I will add a destructor. I'll call it on test, which let's call it something else. Let's just call it out there. Okay. So what that means is that test is a function that takes an int interfumber and gives you back a test. Out is a function that takes a test and gives you back an interfumber. So what we can do then is when we this fold, the rows of this fold will be a function. So what we will do is we'll just change that to out after fold map test. No, out, yep, that's right, out. Okay, so just to be clear what's happening, because we've really gone beyond what you probably expected in to, but this is extra fun. What we've done is this function, yes, this expression here, sorry, is a list of tests. We fold them and we'll get one test back that will do all the tests that we want, that will do all these tests. Then we remove, if you like, there's a function in there, so we remove the function in there. So this would be a type test. And in fact, what I'll do is I'll show you this in the oh, I didn't build it. No, I'll show you this data constructor. Oh, okay, it should have been, that should be test. Okay, and then now what is it? There's another. Oh, I didn't build it. Oh, it's really annoying. Aha, there we go. So now let's show you this. Okay, I'll start with this. If I do mul2, you see mul2 is interfumber. Okay. Now let's say for the sake of argument we do mul2 in a list. Let's do mul2 and mul3. Okay. Should be the other way around. We'll do that. Let's do T. Yeah. So this then is a list. Sorry. Oops. Is a list of interfumbers. A list of functions that take an int and return a fumber. Now, if I do type map test, and then I do mul2. In fact, what I'm going to do is let mul2, mul3, mul5, mul7, mul9. Just so we're doing exactly what, yeah. And then I do the type of xx. That's the list of functions that taken into, and then I do t map test and then xs. You see, that is a list of tests. So what we did is map test xs converts the xs from a list of functions to a list of tests. Okay, now if I then do for map test, see, that's just one test. So it combines all the tests, the for combines all the tests into one test. Okay, and then if I do the type of out hold, yep, that's just another, that basically unwraps the test and gives us back a function of interFizzBuzz, which we can then apply to our numbers. Okay, so that was a bit more abstract, but what have we gained? Well, we've gained some concision, because now what I can do instead of all this is if I do this, okay, I can put these in line. So, okay, so I put those in line. Then I don't need these anymore. Oops. And I don't need that anymore. Okay. And what I'll do is I'll put this on the separate line so it looks nicer. Okay. Alright. And if I then just build this, yep, there we see everything's still working. Now, if I want to add another case, all I need to do, let's let me add the case for let's see. Let's add the case for 11. Yes. So this 11 is prime. If I just do that, I'm allow 11, and then what shall we call that? Bears. Let's go with bears. All right. After adding that one line, if I now go to build this and then reload, let's go to say 22. What do we get when we see 22? 19, 20, 21, 19, 20, 21, 22. Shouldn't that be? Oh, no, wait. That's okay. It should be. Oh, that's interesting. It's not. I built this out now. Okay, let's check. And if I reroll, yes, I hadn't built it. Ugh. That's the thing, because for example, if we look at say 99, 98, 99, we see we've got bears. FizzBuzz has bears. If I go to 11, you see you just get bears. So you see, to add another case, all we need to do was add one line. So we go to 22, we should get fast pairs because 22 is a multiple of 2 fast, and it's a multiple of 11 pairs. Yeah. And if we go to say 33, that should be 2, 33. Yep, FizzBuzz because multiple of 3 is multiple of 3, multiple of 11. So in order to now to extend this program with other multiples, all we need to do is just add one line. Just add the Molov case here, and we're done. So okay, this was a bit we went a bit more what do you call it? We added a bit more abstraction. So, but you can especially for a problem like this, you probably might have stopped short of going for the Monoid instance. But particularly when you're integrating with libraries and for larger problems, knowing how to being aware of this can be very helpful. Anyway, I think we've pretty much done all enough for FizzBuzz, I think. So until next time, take care.